All right. The last piece here in our sort of hodgepodge unit will be to talk about scatter plots and trend lines. And this kind of goes along with our modeling from the last module, last unit, the last lecture. And that sometimes when we have points in a plane, in a coordinate plane, we want to be able to try to find a linear equation that fits it, or maybe a quadratic, or maybe an exponential, so that we can use those equations to make some predictions. And that's what we're going to talk about today. We need to be able, and we're going to talk about linear modeling today. So we're going to use what's called a scatter plot. And once we have a scatter plot, we want to come up with the trend line, come up with the equation of that trend line, and be able to use that to make a prediction. Okay? So what's a scatter plot? A scatter plot is a graph that relates two different sets of data by displaying them as ordered pairs. Okay, so any two things you want to measure on something or somebody, and you're looking for a relationship, right? So let's say I think that your shoe size is related to how much weight you can lift, how strong you are, right? So I think shoe size is going to be related to how much you bench. So we could grab that data and see what kind of relationship there is. And if we were to do that, we would grab your shoe size and your bench, how much you bench, and that would become a data point for you. And then we do it for a bunch of your friends and plot those data points and see if there's a relationship. Now, there's probably not going to be one there. So instead, let's talk about age of car and how much a car costs. Right? Some of you guys are headed towards getting your license, possibly getting a car, and so that might make sense to talk about. So let's say that you wanted to price out, you're thinking about getting a Nissan Altima. So you want to know, based on age, how much you should expect to have to pay for that Altima. So you go out and you find a bunch of Altimas and you price them, right? There's a 2-year-old Altima that's about $15,000. Then you find one that's 7 years old, and it's maybe $3,000. And then you go out and find one that's 4 years old that might be about $12,000. Then you find one that's 11 years old, and it's about $2,500. Okay? Each of these would be an ordered pair that you'd have to plot in a coordinate plane. 2, 15,000, 7, 3,000, 4, 12,000, and 11, 2,500. Now, we're going to have to scale our x and y axes to help get that done. And we'll talk about that some more in a minute. But I would plot these points and then see if there's some kind of relationship. Now, when I plot these points, I might get something like this, right? And now we got to talk about correlation. Correlation tells us how the two sets of data are related. Now, if it looks like this, then this is a positive correlation. And what that means is, as our x value increases, our y value is going to increase. That's why these points are where they are. Okay? Now, I would, in the case of this car and price thing, I think age would be related to price. I think age might tell me how much a car is going to cost. So I'd put age on the x-axis and price on the y-axis. If I were to do that, then what this positive correlation would tell me is that as age increases, the price of the car increases. And that's not what's going on here. That's not what typically goes on. Okay? Instead, I would probably, if I plotted out age versus price of the car, I'd probably get something like this, because as the age increases on a car, the price typically goes down. This is a negative correlation. It has a negative trend, a downward trend. Okay? Well, some variables that we measure end up plotting out like this. And my guess is shoe size and strength would be like this. Right? To where there's really no trend. Right? I can't find an upward trend, a downward trend, and anything. So there would be no correlation and no relationship between x and y. okay? But we have to plot out the points and see which of these relationships would be true, okay? Now, once we have our data points plotted, and we can come up with the trend, there's some sort of correlation, then what I want to do is I want to use that data to help me predict something. In the case of the cars, I want to take those cars and come up with some sort of model that will help me predict how much a car costs based on its age, how much an Altima would cost based on its age. So I would draw a line, a trend line, and a trend line is on a scatter plot. We try to draw that near the points as we possibly can to show the correlation. You want to try to draw a trend line so that it captures as many points as you possibly can, but any of the points that it's not going to capture, we want to try to make sure we have the same number on the top and the bottom of that line. Now, why are you not going to be able to capture every point? Why are these points not lined up in a row? Well, because in the case of the cars, not every 7-year-old Altima is going to cost exactly $3,000, right? As we use our common sense, we understand that there are the other factors that go into the price of the car. So they're not all going to line up. As a matter of fact, there is no data set that will line up perfectly. So when we draw our trend line, we're going to have to try to fit those data points the best we can. Okay? When we have that trend line, we're going to try to make predictions. So now that I have my 4 data points of my cars, I want to predict how much a 6-year-old Alta should cost me. I found a car, I found an Altima, it's 6 years old, I want to know how much it should cost me. And that'll help me determine if that car is a good deal or not, right? So if I were to do that, then I'd be using what's called interpolation. Interpolation is using the trend line to estimate a value between 2 known values. Okay? So I found a range of cars from 2 years old to 11 years old. And as long as I'm using my trend line to make a prediction from somewhere between age 2 to age 11, and that's where 6 falls, then this is interpolation. In our model, our trend line should be fairly accurate for that, as long as there's a pretty strong relationship. Now, extrapolation is where I try to use this trend line to make a prediction outside of our data range. In other words, if I find a 15-year-old car and try to use this model as a predictor, then now we're outside of our data range. And that can be very dangerous. We are only going to be able to see the data that we have. And so trying to make a prediction outside of that data, we don't know what's going to happen to that data outside of that range because we're not looking at it. So it could be tough and less accurate to try to use extrapolation. Okay? Now, the last definition here, trend lines, you can pretty much draw anywhere you want. There is one and only one line of best fit. And that line of best fit is a trend line, and it shows the relationship the most accurately. It is the best fitting line to the data. Okay? So, once we have the line, we're going to want to come up with the equation of that line to help us make a prediction. So, how are we going to use all of this? Well, we're going to collect our data first, graph the data points after we've made our ordered pairs, draw a trend line, choose 2 points on the line. Now, we're going to choose 2 points. Why? Because if we want to write the equation of a line, we have to have the slope and a point on that line. We find the slope by using 2 points. Subtract the y's over subtract the x's. So we got to find 2 points. Now, once we draw our trend line, we have to use 2 points on that line, right? On the line. Now, that means it might be data points that we use, or it might not. It doesn't have to be. We just need 2 points on that line. Then we go find the slope. We take a slope at one of those points, plug it into the slope formula, cross multiply, and get our equation. Okay? So, let's take a look at what this might look like. So, is there a relationship between fat grams and total calories in fast food? right? So we go to McDonald's and we collect a bunch of sandwiches. We pick a bunch of sandwiches. We find the fat grams and the calories for each of those, and that's pretty easy to do anymore. It's posted all over the place. So we want to graph these data points and see what kind of relationship there might be. And so we're going to have to scale the axes here. Now I think fat grams are probably going to predict calories. So I'm going to put fat grams on the x-axis and calories on the y-axis. Very often it's not going to matter. But if you think that one variable is going to be a predictor of the other one, that's the variable you want to put on the x-axis. This needs to be your predictor. Okay? All right. So we got to figure out how to scale our axes and then start plotting our points. The other thing I want to point out is this does not have to be 0, 0. In a scatter plot, that does not have to be the origin. All we want to do is create a window so that we can see our data, wherever that has to move. And our data can have different numerical values. Okay? I also want to point out the fact that we're not really using the negative sides of the x and the y axis. Why is that? Because you can't have negative calories in a burger, and you can't have negative fat grams. And very often with our data, we're not going to be able to have negative numerical values. So we're only going to use the positive side of the x and the y axis. Okay? Now, our fat grams range from 5 to 34. So I would want to show my graph. My graph would probably want to go from, I don't know, we can maybe even start at 0 and go up to 35, which is a range of 35. And we count the number of grid lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And ideally, we would divide by 15 to see how much each grid line needs to be worth. 35 divided by 15 is a little over 2. So we want to go more than 2, but we wouldn't have to go much more than 3. And I think 3 is going to be a pretty good scale for our fat grams. So I'd want to make this line 3. The next one would be 6, and so the next one would be 9. I'm not going to label them all because it can get kind of crowded. And so here's how we label our x-axis. And then our calories. Our calories range from, what, 260 up to 590, which means I'd probably want to go from maybe 250 to 600, which is a difference of 350. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 again. And so we want to go more than 20, because 350 divided by 15 is more than 20. It's more than 20, but less than 30. So what if we started at 250 and moved up by, well, 30 might be kind of hard. What if we moved up by 50? And this is not an exact science. You can scale this pretty much however you want. But the idea is that you don't make your graph so small that you can't draw a good trend line. So you want to try to use as much of the grid lines as you possibly can, but also be able to plot the points as accurately as you can. Okay? All right. Now I want to use all of these as ordered pairs. So I need to plot 9, 260. 9, 260 would be about right here. Then I'm going to plot 13, 320. 13 would be about right here. 320 would be about right here. Then 21, 420. 21's here. 420 would end up about right here. 31,560 would put us about right. 31 would be here. 560 would go up and put about right here. And then just keep plotting those points. 550, 31,550 would be right below it, right there. 34,590, 34 is there. 590 would be about right here. 25,500, 25 here. 500 would be here. 28,560, 28 would be here. 560 would be about right here. 2440, 20, 440, and then 5,300. 5,300. So we have our data points plotted. Now we'd want to try to come up with a good trend line, right? Draw a line through your data. Your line might be different than mine, and so that's okay, okay? Because we're just doing this by hand. So I would draw my line right through here, okay? It's wherever you think it fits the best. Now, just so happens that when I drew this line, my line went through this corner and through this corner. And so those are the 2 points I'm going to use. And if you notice, they're not data points. And again, that's okay. We can still use those points. You can certainly use a data point if you feel like your trend line goes through one. Maybe I could use this one. But I found 2 nice corners. I'm going to use that. And so my 2 points that I'm going to use are going to be at 18, 400 and at 33, 600. And now I need slope. So I can start to write the equation of the line. Subtract the y's and then subtract the x's. So we're going to get 200 over 15 okay, which I could divide out and get a decimal, but right now I want my slope to be a fraction, so when I put it back in the slope formula I can use it to cross multiply. So I can reduce it down to 40 over 3. I'm going to set this equal to, pick one of your points and plug just one of your points in now to the slope formula. So y minus 400 over x minus 18, and here's what I'm going to cross multiply. So I would get 40 times x minus 18 equals 3 times y minus 400. Distribute, distribute. So 40x minus 720. Distribute, distribute. 3y minus 1200. And then we're working on getting y by itself. So add the 1200. And we would get 40x plus 480 equals 3y, and then divide everything by 3. And here's where I'm going to go ahead and divide it out. I want the decimals now. It'll be easier to make my predictions with. So 13.33x plus 160. And so that's the equation of my trend line. It might be a little bit different than yours, and that's okay. They should be pretty close as long as you're using 2 points that are reasonable points on your line. Okay? So, why do we have that equation? Because now we know that McDonald's is going to put another sandwich on their menu, and it has 22 grams of fat, and we're very interested in knowing how many calories it's going to have. We try to predict how many calories it's going to have. Okay? So, since we have this equation, we can use that as our predictor. So y equals 13.33x plus 160. And since fat grams are on our x-axis, we're going to plug the fat grams in for our x. So 13.33 times 22 gives us 293.26 plus 160 . And so we think the new sandwich is going to have about 453.6 calories, or about 454 calories. So now we know how many calories we need to burn off if we eat that sandwich. Okay, that's a lot of calories. Now, that's to do the trend line by hand. We can use technology to help us come up with our trend line a lot more accurately, find the line of best fit. The only way we can find the line of best fit is with technology. There's a way to use your graphing calculator, and I would have to show you that, so feel free to come in, and I'll show you what it looks like on the graphing calculator. You're not going to have to worry about doing that, so don't worry about it. But one of the things that you would get out of a graphing calculator is R, which is the correlation coefficient. The correlation coefficient tells you how closely the equation models the data. The closer you are to 1 or -1, the stronger the relationship is, and the more lined up your points would be. Obviously, +1 for a positive correlation, -1 for a negative correlation. In the instance of our burger, we'd be looking for a correlation close to 1, because we know that as the fat grams increase, the calories are going to increase. So it's going to be a positive correlation. And as a matter of fact, if we were to put this into our calculator, the correlation coefficient was going to be 0.974. So that's pretty strong. Okay? Last thing here, causation. Causation is when a change in one quantity causes a change in the second quantity. Okay? A correlation does not always imply causation. Okay? Between fat grams and calories, we're pretty close to being able to call this correlation to be causal. In other words, we're pretty sure from this relationship that if you increase the fat grams in a sandwich, then you're probably going to increase the calories. There's a good chance you're going to increase the calories. So an increase in fat will cause an increase in calories. But there are other things that might show a strong relationship but not be causal. For example, go back to the shoe size and strength example. As a matter of fact, that would probably be a negative correlation, and maybe even a pretty strong one, because the bigger the shoe size, the taller someone is, and it's harder for tall people to be able to lift as much. So they might be able to lift less weight than someone who's a little bit shorter and has a stronger center of gravity. We'll call it that. So that would probably give you a strong negative correlation, but shoe size and strength really doesn't have anything to do with each other. So we're not going to say that your shoe size causes your strength. A better example here would be the number of mailboxes in a city and the number of firefighters. There's going to be a positive correlation there because if your number of mailboxes go up, that means that your population is larger, and so of course you're going to have more firefighters. But just because you put one more mailbox, all right, so I got cut off there, and I'm not sure exactly where I ended up, but so we'll go back over this real quick. A causation is when a change in one variable causes a change in a second. Here, our fat grams is a strong correlation, and we're pretty sure that if we increase the fat grams, then it's going to cause an increase in the calories. An example of where causation might not exist is between the number of mailboxes in a city and the number of firefighters. Right? As the number of mailboxes increases, the number of firefighters will probably increase also, because that means your population is larger and you're going to need more firefighters. But just because you add more mailboxes, it does not necessarily mean that you have to add firefighters. So there's not going to be a causation there. Okay? They just happen to be related. Okay? So anyway, that wraps us up. If you have any questions about this stuff, come see me. Otherwise, your homework's out in Canvas. Make sure you get that done by next time.